Okay, we start recording. First, questions, discussions. So open discussion.
I have a quick, let's say, question.
Yeah.
In case of next, let's say, work like the one yesterday in groups, could you please allow us like 4 to 5 more minutes?
Oh yeah, absolutely. We have just another exercise today, and yesterday it was just to experiment. Well, I can, in any case, open again yesterday's exercise, and we will discuss together, of course. Okay. So after the first part of this this class, we'll open again yesterday. Okay. No, I can't open with the same groups. So we will discuss all together the yesterday's exercise. I have a new exercise today that is more complex, and so I will give you more minutes. And so I think it's important. They are so we are not facing. Correctly the programming so far. We will start next week. Since next week I will describe in details every single system call and give you examples on how to use a new exercise. This is just a sort of experiment to see if to get familiar in advance with the exercise. So it's not so important to solve completely. In any case, you're correct. I will do what you suggest. Other questions about the overview of the kernel and any other matters? So we can start. Where is it? No, this is not this. Let me check where it is. Okay, memory management was here. So let me resume Zoom again. Share the screen. It's strange, but I can't find. I can't find the screen to share. Okay, I found it. So you see the memory management slide? Do you see?
Yes, I can. Yes.
Okay. It was the couple of slides that I dropped yesterday. Memory management. Well, paging and memory management. So the best thing that it can do is to just to share another file. I told you that it's a bit chaotic session. So, okay, I will try to give something on this screen. Okay, memory. The memory.
Sorry, I don't see the sheet.
Oh, fine. So, fantastic. Stop share. New share. Okay, now you see.
Now I
Yes,
see,
now it's
yes.
good.
Fantastic. Virtual. So memory is in any case virtual memory, even in very small microprocessors and everywhere. Virtual memory means that, as I told you yesterday, that you have the code uses all address space. If you have a 64-bit machine, you have 64-bit addresses. And this is, and it's a user space, completely separate, hardware separated by the kernel space. The kernel space is another space of addresses that are completely different, and there's no communication. Only the kernel can communicate between the two spaces. And for example, during input, output, or using peripherals on any kind of device, continuously copies data, for example, coming from input, and data coming from input read from the hardware locations into the user space. And this carried out by the device drivers. Device drivers are exactly those interface codes inside the kernel able to transfer data from the external and kernel space addresses into the user space addresses and vice versa. When you output the data, or you send the data through the internet or everywhere, or also inside the buses inside the machine, you simply transfer data from your user space in memory of the user. The user gives the data to a system called for input output, and we will see that the code for input output we are talking about will be write and read, the basic system calls for transferring data from user space to system, to kernel space. Internet connection unstable. Okay, now you can see and hear.
Yes, yes, you didn't froze.
Okay.
Yes, just a bit slow.
Wow. So I told you that we will see the first system calls will be write and read. But read are the basic system call to transfer, to interface data between the user space and the address space of the user and the address space of the kernel. And the kernel uses provides the further transfer to the hardware, or from the hardware to inside the kernel. And this is carried out by the device driver. So now you know what are the device drivers for, what they do from the point of view of the semantic of the space. So the code in a virtual memory, your code has the availability of the full address space that is huge. So in general, much more than the physical memory. And many codes owned by different users do the same. So each code by each user thinks that it has the availability of the whole address space, and all codes think to, or believe to have the same power. This is carried out by the mechanism called the virtual memory. all machines are based on virtual memory. So we are not saying, describing concept typical of the system. Oh, the basic idea is let's change color. That the basic idea is that we have a process. With the data, stack, user area, and text, with not concerning that. One process, two process, and so far. When you compile the process, typically these segments of code have similar addresses, but it has no importance at all. So they can be everywhere. Usually the compiler starts from a conventional address that is 0 or 1, it doesn't matter, so low addresses, but these are dummy addresses that are changed dynamically. Then when you load and execute the process, here is the memory. With dotted line because physical memory. And this is virtual memory, since we don't have those addresses, but those addresses are already, can be used by your processes. So a mechanism, a hardware mechanism based on tables, gives this process some segments that usually are called pages. We don't know where, doesn't matter. Why so not joint spaces? Because probably the memory is already loaded by other pages of other processes. And so when this action is at first run. So when you ask the shell, when you simply give the shell the name of an executable file, a mechanism starts inside the kernel that is load and run. And doing that, it partitions all the addresses in pages. Nobody perceives the difference between pages because the hardware mechanism, there is a table that makes the code to use automatically the addresses as if they were in sequence. So during execution, you cannot know what is happening and why the pages are put in real memory. Maybe that your program is so big that some page is here or should be there. So what we do in this case, we will see. The second process has another at run, and load and run as different locations. Suppose it is small, it's smaller, okay. And this happens for all processes running. So the memory is divided into single pages. The two mechanisms shortly described or in the slides are, well, one is not described in the slide, the one that I called the load and run. The first decision about where to divide and to locate the pages. And then you run your processes. Well, what's happening? You have seen that in the operating system, usually there are hundreds of processes. Many processes are daemons or services run directly by the operating system itself, and there are several processes. When a robot program is a concurrent program composed by many nodes in the ROS terminology. They usually are processes and service processes for communications and so on. So maybe that for doing, for doing all that, sometimes the memory, the physical memory is full. You need a page here and there's no additional room. So there are two mechanisms or two logical components that are called, let me choose the black, two basic daemons or services. One is the page daemon. It's a service that continuously checks if the memory is loaded with the pages of processes that are not running, typically waiting processes, suspended processes since a long time, and following a special algorithm, it decides to free the memory. Frees the memory. Frees space, finds new space for loading new programs or for loading new pages. The other one is the swapper. With the two action in, out, and interacts with the secondary memory, typically the hard disk. So in case you need space, and the page daemon does that very often, it stores pages, downloads page from memory, and puts a copy of pages that are no more needed. This can be done usually, not written in the slides, is a detail, but maybe a curiosity that can be interesting to you. It can be done in a special file system. So a part of the disk device devoted exactly to do that, but you cannot access as a user, or can do in user space or user space file system. So in regular file system, the difference can be seen very clearly in Windows. Since 20 years, the swap area is in your file system and occupies a lot of space, gigabytes of space, because it helps the physical memory to behave like the virtual memory. The virtual memory is so big that theoretically you need enough space to store all the memory of all possible processes that uses the whole address space. It doesn't happen so. So usually the user space file system is few gigabytes and it's enough. So the same amount of the physical memory you have in your computer. Or in traditional Unix Linux, there is a special file system you cannot access. But now in recent Linux, it is also possible to do this in user space. There are drawbacks and pros and cons. The two solutions were not interesting for us. The idea is that you save the memory, and as soon as the process needs again the pages that have been swapped, they are loaded again. For example, if a process is in state waiting for a long time, its memory is swapped out by page daemon, so freeze memory. And as soon as the process gains the CPU, goes through ready and then running state, its pages are taken out from the swap area. This is called the swap area, and put again into memory. This mechanism, I focus on this. This is the total explanation. What is interesting for us, roboticians and real-time programmers, this process has two drawbacks. Let me write here in gray. Two drawbacks. Takes a long time. Takes a long time because the secondary memory, particularly mechanical hard disk, but even a solid state hard disk is much slower than memory. So even if the copying the memory in and out is is fast, is the physics of the secondary memory that makes the mechanism slow. And the second point, why here? Here, the second point is that you write on disk. Writing on disk maybe is a weak point in general for a system that must be safe and reliable, like a robot or an automation, critical automation system. Imagine some other situation, for example, an airplane in which your program controls how the airplane stays and flies. So what's the problem? Every secondary memory, every hard disk, be it mechanical, either mechanical or solid state, has a limited life with if compared with the central memory. So you must limit the number of writing, and in particular, solid state disk has a shorter life with respect to hard disk life, in particular when you write. So you have to limit the number of writing on hard disk. So this is a reason why. This is the reason why usually in robotics you don't want to swap. Robotics, automation, critical automation system, no swap. Swapping is maybe dangerous and not only make the system run much slowly than normally, but can be dangerous. So what are the techniques? The techniques for not swapping are, one is just to be sure that you have enough memory to for which you don't need swapping itself. But so it's a sort of general design of the system. And in every kernel is possible, even in Windows kernel, is possible to stop the swapping system. So you can decide that swapping does not happen. It's easier in Linux because you simply stop the swapper, the page daemon and swapper. And in this case, there are no swapping, but sometimes you cannot run a process. And in general, remember that when you write a program, you use dynamic memory. So you can decide in advance which are the dimensions of the codes and data of your processes, but it is difficult to foresee how much the dynamic memory grows. And so it's not so simple, and you have also to write monitoring processes just to prevent that. Last remark, the mechanism of, there is a signal related. There is a interrupt more than a signal, interrupt, but raises also a signal. In case a process want to address a page that is not loaded in memory, because not yet in memory, because you are not using this, or had been swapped out, or by the page daemon and swapper, or is in virtual memory, so is waiting to be loaded in normal memory. This is called the memory fault. This is an interruption that is raised by the hardware that manages the memory. It's not a fault in the sense that is an error. Simply, you don't find the page you need because it has been swapped out, is not yet swapped in, or needs to be created in physical memory since it is in virtual memory. Memory fault is just interrupts the execution of the process and makes the page daemon and swapper to run, and the memory fault has the only effect to put the process that is running in wait state. Wait until the page it needs is loaded again and is ready to go. So memory fault is another interrupt, like any other interrupt, that makes the switcher to decide which is the next process, basing on priority and so on. These are concepts that in case of strict real-time situations must not happen. So memory fault and swapping in real time must not happen. Let me pause for a while because maybe there is something. No, nothing. No emergency. Okay, that's the synthesis, very short and fast and with all concepts underlying the memory management. Just to know that this is something that must be taken into account by a robotician programmer, because this affects very highly the speed and reliability of programs. So it must be taken into account.
Excuse me.
Just the last remark. This is also one of the reasons why programming languages strongly dynamical and based on completely on dynamic memory like Java are not often used in real time or in robotics in general, because using as well as use the dynamic memory in C++ or C, is the same thing, but in C++ is an option that is not necessary. If you have a language completely based on dynamic memory, it's very difficult to foresee what happens in demanding pages of your program, because it depends on the garbage collector, or the dynamic memory and so on. And this is is strong conflict with the mechanism of virtual memory swapping in, swapping out, patent, and so on. So this is an explanation why Java, that is a very good language, it's hard to be used in real time, even in non-strict real time context. Sorry, just finished. Okay, questions?
Yeah. May you repeat what means takes a long time?
Takes a long time. Well, a long time. Where it is? Takes a long time. Swapping in and swapping out. As I told you, when this process needs a new page that is not here, suppose that only this page has been erased from memory by the page daemon because it contains data that are rarely used by process one. So it's an old page, and the page daemon, for freeing memory, decides to not to erase the data, of course, but just to swap out this. And suddenly, process one needs data. In this case, it addresses a page that is no more in memory, an interrupt signal, that is the page fault or memory fault, well, page fault. Well, I made a mistake. The correct name is page fault, not memory fault. Memory fault recalls errors, no, page fault. The page fault interrupts the execution of process one that was running, now is waiting, and it takes the time needed, that is a long time, is the time for freeing again the memory. Probably this space is not yet available. So some other page must be swapped. There is the reading, writing to from disk, loading memory, and waiting for the new, for waiting that the switcher gives the process one that has been interrupted priority enough to be run again. This takes a long time. It's okay. The series of steps. There are many steps, and each step takes a long time. And in particular, the swapping in, swapping out. Not only the time just to physically read write on the disk, that in solid state disk usually is short, not so short like reading from memory, for example, but in any case, it's short. But all the process of rearranging the memory. So it's a dramatic situation. So I don't want to exaggerate, but using this way virtual memory that has been designed for time-sharing users, not real-time users, is something that is the opposite with respect to requirements of a robotic program. Okay. Well, sorry for the figure that is a mess, but you have on your slides. I will try to save. I'm not sure to do that. Okay. So I can say that the slides, the theoretical part of the description of the kernel is finished. We should have something to say about the file system, but we delay that description to the moment in which we describe the write read primitives of the operating system. Okay. Well, questions? Either I forced you to sleep or I've been very clear. So in any case, we can just rest for 5 minutes, okay?
Okay.
5 minutes pause. Pause recording.
Yeah.
We start. Questions? So let's talk a bit about the yesterday's okay. Can you see the code?
Yes, it's there.
What the code that I gave to you yesterday, which is the NeuroWeb. The original code is this one. So you see, there's no differences. The code that I compiled and run. The only difference was just the number of include files. Let me spend just a few words that in advance because we will meet them. C coders know perfectly what they mean. In POSIX, there's a lot of include files, of headers or header files. I will show you a table, and depending on the kind of system call you're using, there are specific include header files. The classic stdio must be included in any case because it provides definitions for printf, scanf. For example, you see types that are used for system types. In this case, I don't remember which kind of system types we are using. Yes.
PID_T.
PIDT. PIDT. It's a redefinition of integer and so on. So you will learn which kind of system headers you have to use. Without those system headers, you could not compile. So it was just a trick for preventing you to directly compile. Let's comment the code. We can so this code is as a main, the main with the classic interface. We are not using the interface, but is correctly declared. Variable counter and so on. So it forks. So it's a main that simply forks. As soon as the fork is called, as you have seen in the slides, the kernel generates a copy of the whole compiled code. So a new process, exactly the same. The only difference is that just after the fork, you can check the return value. These two lines must always be included in your code. And in general, lines of this kind, they are error checking. In particular, in robotic programs, you always need to know what happened. In general, in concurrent programming, you must. It's very difficult to debug a concurrent programming by simply running it. So it's very important that every time you call a system call, you check the correct execution of the system call. In that case, the check is simple. If the return value is less than 0, it means error. Which kind of error and why, we will discuss. Several situations may occur. There is also the possibility of distinguishing between errors and the P error that you see here, we will quote, will describe correctly. This is really important. Is a system call that not only alerts you and writes you a message, in that case fork, but also has the possibility of storing the kind of error in the bug file. So it is the interface with the concept of a log file that I have presented just in the first slides, in the very first days of the course. So P error means print error. Is not simply an output instruction like cout, but just is the interface with logging with the kind of error. So, and return -1, return is directly compiled. It invokes a system call that terminates the process. We have seen the concept of terminating the process, returning to the father process, right here, returns to the father process -1. So when you exit from a process, the process is deallocated by the kernel, but it gives you back a value just like a function, a limited number of possible values. There are integer values, negative or positive or 0. Conventionally, 0 is okay, and other numbers may signal you severe errors. And return to the father process. A question for you all. Which is the father process of fork.c that we are considering?
Is it the shell, maybe?
It is the shell, exactly. The shell, we have seen in the short lines of code that the shell, when you say run fork, this program, this process, forks and executes this program. So the shell is always the father process of all the processes you are activating, you run interactively. So just after those lines that were just to end in the shell, I will show you, there is the possibility of checking which is the return value of a process. It's very useful in debugging. So nothing interesting here, just error management. If child is the value of the variable child is 0, if this value is 0, you know that is the copy that runs at that moment is the new copy. So we call conventionally the child process. And executes simply a function, body, with the parameter that is the string, constant string child, and after executing this, returns 0. So exits the child process, returning 0. Conventionally, as I told you, the same, return to the shell, the value 0. There's no else, and probably would be more clear writing else. There's no need of writing else because this branch of the if exits, returns. So this is implicitly the else part. If it is not 0, this is a running copy of the father process and calls this function with the string father. And then the father issues a system call that is called wait. Not so important in this case, but it just, well, it has no effect it's a small effect, very small. And so the father does not exit immediately, exits after the son has exited or has died. If after wait rest we had written some messages, you had seen that the father was waiting. In this case, it's just a temporal waiting, enters 0. What is the meaning of the function body? The function body has in input an array of characters, char star as string, and loops into the string and writes the string several times, and with the increase the string. Well, sorry, writes the string saying that which is child or father who is writing, because both the father and child have a copy, a private copy of the function body. So each one writes, in this case, 5 times the string, the number counter, incrementing the counter, and preventing to write immediately, they wait 2 seconds before. Sleep is an important system call for debugging and for doing exercises and so on. And this is the effect. We can see which is the what happens when you do not sleep, for example. So questions about this? So I think now that, okay, so close. I need a shell. Okay. I need a shell so I can let me get inside the shell and you see the shell?
Yes.
Yes.
Yes, it is. Okay, so let's do a shell exercise. And I keep on apologizing for the bit chaotic class. In any case, we do in the directory now, so we have to do something. So the directory in which I'm working is on the USB memory stick, so I know where it is. When you write a string, you can push tab before finishing the string, and automatically the shell, the bash shell, tries to find the name that matches what you have, what you are writing. For example, RE tab. The shell automatically completes Renato. If there are more than one name in the directory that matches the prefix you're writing, the shell will show you and let you show which is the one. This is a directory in the file system in which external devices are mounted, USB mounted devices are mounted. So that's the reason why this strange path. Let me see the name of 43, okay, the CD 43, so on, okay. Then for example, okay, just A matches different directories. And if you press, they are shown. So the ARP, okay, Robot Programming Method Robotics. Okay, let's see where we are. It was in week 3 and week 4. No. Oh, I'm sorry. Many of you know what it means, but ... means the one level up. So I am again in the father directory, and I go into the 3-week ls fork.c. Fork.c, let's see if the new version, just less fork. Okay, with no sleep. Q for exiting by this interactive reader of files. GCC, fork.c. Okay, compile it, and the name of the executable is a.out, so it has erased the previous a.out. So you see that in this case, without the sleep, one of the two processes have been able to complete its loop. And well, with the arrows, we can browse the previous previous commands given to the shore. I'm just pushing the arrows up and down, so I can find the previous command. So instead of okay, so you see that in that case is sort of deterministic execution, and this means that the switcher, so the scheduler, considered the father still running before the control is given to the child. It's it's normal to do that. The father issued the system call, and before the time expired in which the kernel generates a new process, the father is able just to carry out completely the execution of the 5 loops of the function body. If we, I use, but you don't do that. But I'm an old programmer, so I use the old instruments like Vim, a fantastic instrument for this. Completely, you must use keys, but don't use this. It's complex. So we put again the sleep. In this case, you see that 2 seconds of pause change completely the logic of the scheduler, and so it is able to give the control to one of the two processes. Okay?
Sorry, sir.
Yeah?
How can we know the time that the process has to sleep? For example, 2 seconds or 1 second.
Well, this is in this case, we will see how sleep works. In a previous exercise that you have done, and I've asked you to trim the values to have an output. The exercise in process that are completely not synchronized. You remember 1 week ago, we used the sleep instead of the sleep. Sleep is a primitive that has only seconds as parameters. So you cannot specify half a second or 1/10 of a second. So it's a very rough execution. In this case, we can see the difference between 1 and 2, but probably there's no difference. From the point of view of the scheduler that acts in milliseconds, 1 second, 2 seconds, 10 seconds is the same. We have the same output. You can do this by using the sleep instead of the sleep, and try and see what happens. Try yourself using the sleep like we did in the previous exercise, and you can specify even nanoseconds. So you can disturb the scheduler and see which are the differences. Okay?
Okay.
This was an exercise. Now I want to give you another exercise like this. Well, before I do that, since I have an open, we have no time. The exercise is already in Aula Web. And so, sorry. I can, let me go. Okay, this example. Okay, this one. Can you see the code? Yeah.
Yes, we can. Yes.
Yeah. It's in Aula Web, in the Aula Web for today. In this case, I did not erase the header file, so you can also compile, of course. But I push you to understand the code and foresee what happens in 2 cases. What is expected to do as it is. So with the many lines in comments, so do not compile it. And in second case, if you remove the comment, and what can be the difference in the execution. In this case, just for known delicate C coders, you see that also in this case there is a main that calls directly a function that is called spawn. In this case, the spawn function, differently from the previous case, forks and execution. In one case, with the comments, directly calls the exec. The exec is a system call we have seen very briefly that instead of producing a cloned copy of the same process, substitutes the process with a new process. And the process is a new one. And you can pass the process arguments with the normal interface, like in C language with the argc and argv. We are two
Excuse
cases.
me, Professor.
Yeah?
I have a little question. Exec. What does VP stands for? Except VP.
Oh, exactly, because we will see that exec is a family of different system calls, but the only difference is the way in which you pass the executable, the arguments. So it's the classical C standard interface of parameters, argc, argv, okay? There are several ways different ways of passing arguments. This is one of the simple ways, and you see that is the way of passing arguments is of composing a vector, a string vector, in which there are these three arguments. So there are three arguments exactly as you can do by executing from the shell a program specifying three arguments. The first is the string /bin/ls, that is the ls process listing directory. The second is the string -lat. There are arguments for the ls, lat, in particular extended directory, including all files and sorted by time. The four arguments, not three. The third argument is just dot, the string dot. And the last argument is null argument, so a null pointer. And this is the reason why you use that, because it's simple to compose the arguments to pass to the executable here program. Okay.
Okay, and null is mandatory.
Null?
Isn't?
No.
Okay.
No, not in this case. Null is to say that you can write a lot of null, of course, but simply they fill the interface with the executable argc, argv, with the null strings. In the two situations is that in one case, when you don't have this line are not compiled, you directly execute the program. So the running main is substituted by the new executable. In that case, the char star arg list is simply a char star vector of a char star vector of characters, so a vector of strings. In case you erase comments, you first fork, and then the one of the two, the child returns, and the father is substituted. So it seems to be very similar, but if you compile in two situations, there is something different you can do by yourself. So we have not much time. We spend the last 10 minutes in groups in doing that. So discussed like yesterday in different groups, and we will meet next week. So, well, at the end, you will return and we say goodbye to everybody. Now, breakout rooms. Okay.
I suppose nobody is here.
I wasn't here.
Professor, I have a doubt. That function called p error,
That function called
p error, is that a predefined function?
p error. P error.
Is that a predefined function? Because I couldn't see any definition of that function.
No. We will see. We will see next week. Don't worry. It's just to check error and report errors. So you will see what is it for.
Okay. Since in our current program there was no error, that's why we don't use that function.
Don't use that. Not now.
Okay.
Okay, I hope you have enjoyed the experiment. We will discuss next week, because next week we will start analyzing all system calls, and so we have also the time to discuss the example. There's some tricks inside that are really interesting. Well, okay, I will open as every week the meeting on Saturday at 9 o'clock. I simply, for any reason, join the meeting, and I ask you if you want to participate, just to connect to Zoom at 9, because after sometimes when discussions and questions are finished and so on, I will close the meeting. Good. So we can say goodbye. I apologize again for the sort of...
Don't worry, Professor.
But I hope that we'll resume my internet connection at home. Otherwise, I will live here in university. So, okay, bye-bye. Thank you very much.
Thank you, Professor.
Thank you, Professor. See you soon.
Have a nice
Thank you,
day.
Professor.
Bye.
Have a nice day.